It didn't say anything. Wow, normally it said. There we go. I had the volume off. That's why I couldn't hear it. Hi, everybody. I don't know if you were talking at all. You might have been. I had volume off. This is going to be on Big O notation, code efficiency, and stuff like that. We were going to do it yesterday. There's a little more I want to do on exceptions and error catching. I think I'm going to throw that in somewhere in here. It leads into hash functions when we do it. So I got some time to slip it in. But today we're talking about sorting, algorithms, and Big O notation. So let's just click on it and see what we got. We will use this in a second. I'm going to pop it. Oh, let's look at that. Sorting algorithms right now. I actually think that I have that open. Oh, by the way, for those of you that are interested in NASA and stuff like that, I put up a link. I got an email recently. It's worth reading. Oh, look at that. My dumbass didn't give it a name. Let's give it a name. The NCAS program. Being with NASA. Wow. Being a student at COS. It's worth checking out. I was an NCAS student myself. I was the first generation when it first came out. Big shout out to Dr. O. He encouraged everyone in the Mesa program to participate. I was the only one that did that first year, first semester. And I was telling everybody about it. Now it's a thing. We get 10 to 12 students every semester working on it. They do it like once a semester, but once you're in Calc 1 and going higher, and presumably you've been in Calc 1 at least to get into CSCI 2, it's worth checking out. Ask me more about it in class when we're face to face. Today we're looking at code efficiency. So when we think about like how can we make our code more efficient, some ways of looking at it might be like how long is the program? Did you take 100 lines to write? Did you take 120 lines to write? Is it nice and short, easy to read? Stuff like that. That's generally a lot of people's first thought. The less lines, the better. And that can definitely be true. Condensedness, conciseness is definitely a desirable thing when you can. But like, that means not having a lot of room for lines for comments and stuff like that. And commenting code is a really good thing too. Commenting code doesn't cost the computer any more to do, and yet it makes it longer. So maybe looking at how long the program isn't the best approach. We might look at how long did it take to write. We're often thinking about time when we're thinking about efficiency things. But like how long it took to write, you just might not have had inspiration hit. You know, a better code could take a lot longer to do than a shorter code. And let's be honest, most things that take longer to build tend to do better. Whether or not it means there was more thought put into it, or it means it's bigger and there's less errors possible in it. How long it took to write isn't necessarily the best idea, but time is often how we measure importance of things. No one likes a computer program that you click run and it fucking takes forever to run. No one likes loading screens. Now, y'all may not be familiar with this, but there were several video games in the day, like even online, MMO, online games, where there were loading screens just to go between area to area, like EverQuest. EverQuest, you to zone to a next zone, it took a really, really long time to load. Loading it sucks. So we measure stuff on time. So maybe how long does it take the program to run? That seems like a pretty good idea. The problem with timing how long it takes like two different codes to run is there's a lot of variables that come into play. How hot the computer is, how cold it is, has it been rebooted recently? You know, is the memory empty? Are we on looking at running on different computers, different processors? Every computer, every processor runs at different speeds, has different clock times. And so how long it takes to run, it can even vary on the same computer based on how much memory is being occupied by programs running in the background and stuff like that. So clocking how long it takes to run uh, isn't always the best idea, but we can kind of there is something that does work, and we can measure because we know we can figure out how long it takes certain actions in code for the computer to do. And it turns out comparisons like is x greater than 3 is some of the most time sucking uses of code that there is. Doing comparisons really takes the longest. The computer has to think rather than just do. It has to check. So doing comparisons takes the longest. So one way of doing it is seeing how many ways or what's the best way to minimize comparisons. And that's what we're going to do. We're going to look at counting comparisons. Okay. A couple ways of doing that is things we like to do it on is on searching and sorting algorithms. You might like this a lot. I think this is pretty neat. Add that up over here. So you click on this link right here, and it's got a bunch of sort methods. We've actually used bubble sort before in class on different stuff, but like you can play one at a time. It's got each row. This row is like, this is on a block of data and how well we sort the data. Pictured here is the data is based on length. Like how long is it? We want to sort it from shortest to longest. In ours, we may want to sort on alphabetical or numerical or something like that. But we could have the data is like in an array is just randomly is jumbled. It could be almost already sorted already. It could be sorted, but sorted backwards, the reverse sort. Or it could be that there's a whole bunch in there, but there's a lot of repeats. Like if you look at few unique, there's a bunch of bars that are the same length. It looks like there's only really 4 lengths here. There's 1/4, half, 1/3 or 3/4, and full. So how does it sort something where there's a whole bunch of repeats? This is pretty cool. We can watch it. It's worth clicking a couple times. We can see how quickly they go. And you can see how the different sort methods work. And heap and quick, heap's done really quick. Quick 3's really done really fast. Selection looks like it was the slowest. Let's see that again. Heap and, oh wow, merge was done pretty quick too. I don't know which one it shell, merge, heap, or quick 3 was the fastest. Where did bubble show up on that? Bubble's one of the slowest. In fact, it was the second slowest. We're going to take a look at doing this counting comparisons thing in, let's do the bubble and quick 3. Where is my visualizer? There we go. I got a bunch of written on notes as I've taught in here. Maybe I should clean my office. That's a good idea, Jones. Just to grab a pen and being a pain in the, here we go. So we tend to like to look at like worst case scenario. That's a little hard to read. Just write a little bit bigger. And green. Oh, this is empty 10. Excellent. Worst case scenario, best case scenario, and maybe average. And depending on what program it is, we'll take a look at it, each one while we're doing it. You can see when we're looking at these, some of these get their stuff done quick. Like nearly sorted was the first done for insertion by a long shot. And reversed was the slowest for some of these. Look how quickly nearly sorted is for that one. It's done like instantly. And now look how long nearly sorted is, almost the longest for the selection sort. So you have this open, you can come over and you can click on any, that wasn't supposed to happen. Click on the word. There we go. And it will take you over and show you algorithms for it. Each of these, but it doesn't like have it in a specific language. So it just says it. Let's be lazy. Let's look up bubble sort, and we're just going to look up bubble sort C++. We're going to devise our own. We're just going to copy. Let's take Geeks for Geeks. And let's see what it says about the bubble sort array. Fuck. No, I don't want to register. No, I don't want to sign in. All right, so bubble sort is the simplest sorting algorithm. It works by repeatedly swapping the adjacent elements if they're in the wrong order. Doesn't by pairs, that makes sense. So it just goes, are these two in the right order? If not, switch them. And then I'll keep doing more passes until that it sees that it's right. So that's like sorting the way we think of it. Here's an implementation of the bubble sort. It can be optimized by stopping the algorithm if the inner loop didn't cause any swaps. So that's probably this part right here. If swapped equals false, break. This says this is the optimized bubble sort. So let's come down here and let's copy this bit of code. Oop, too far. Now we'll put his thank you, Shivan, for your contribution. We are using it in today's lecture. What did it include bits? What? All right, let's change this to some shit. We want to include the IO stream. We want to write this, adapt this to what we use. Include the IO stream. Include the STD library. What else do I normally like to include? C standard library. That's how it is. We got using namespace STD. That'll work. It's got a C out. Good. So it's got a couple functions. It's got the bubble sort, which just changes them in order. And if no two elements were swapped, it speeds it up. It doesn't keep going through the loop. Breaks it. Simple print array. And it sets up an array of, looks like 1, 2, 3, 4, 5, 6, 7. Look at how they do the size, how they find n. They do size of array over size of array 0. So they're doing it off, this is like how big is the array is what this is doing. They know it takes a fixed amount of memory for each integer. So fixed memory for each integer. And so they just see how much total memory divided by the memory required for each integer. And you can find the size that way. Or they could have just, that's if you don't know the size and you don't want to count them. 7 seems like they could have just counted it. But if you wanted to change this array size yourself, like let's throw some more shit in here. And now I didn't count them. I don't know how big it is. Let's just give it a run. Sorted it. Maybe we'll do a new line in here. Another new line there. Okay, so the idea of checking counting. Maybe let's do an array of our own choosing. So we can like discuss ideas. So we can, let's make an integer array. I don't know, let's make it 10. And let's do one where it's perfectly sorted already. We'll call this option A. Option B, int 10. We'll do a reverse sort where it's already sorted but in reverse. Yeah, it took less space to write. It's weird. And then let's do one where it's like random. We got a 7, we got 9, we got 1, we got 2, we got 10, 4, 6, 3, 8, 5. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, I got all 10. Now, I don't know which one's going to be the best option. We'll try them one at a time. But like we saw when we clicked run, it was almost instantaneous. So let me code these up real quick and we can always comment them out. Seven comma 9 comma 1 comma 2 comma 10 comma 4 comma 6 comma 3 comma 8 comma 5. Why don't we just say constant size 10? Then we can skip this shit. I like it, it's clever, but we don't need it. And array A. Let's do int array B size. And array C size. Wait, we'll call this array sorted. Array around reverse. I can do an algorithm to speed that shit up, and we will. Do a for loop to auto populate those. Print I equals 0. No, we'll start at 1. I less than 11. We want it to go up to 10. I plus plus. Array sorted I equals I. And array reverse I equals size minus I. Nope, size plus 1 minus I. And then we'll have 3 bubble sorts here. We got array random. We haven't implemented the count thing yet. I just want to make sure I got my print thing going on. Make sure we got everything set up so we can test it. Sorted. And reverse sort. All right, let me hit run, make sure this is working. Oh, I broke some shit. What did I break? I'm trying to include something that isn't there. Why? Less than 10, maybe? What the fuck? I want an extra slash n in here. The last one's not doing a... Oh. Why is that doing that? Oh. I didn't start my index at the right fucking spot. There we go. Since I said I equals 1, the array doesn't start at 1. Nope, still pissed. And that shit didn't even work. All right, let's just do 0. Maybe we'll go 0 to 9 rather than 1 to 10. Why is this last one? Oh, size minus 1, minus I. All right, so they all now have a 0 through 9. Okay, so this is how we do the comparisons. This is how we check for code efficiency. What we got to go in, and it might be easier to look at on a little printer thing over here. Things that generate comparisons. We're looking at things like x is less than 5, x is greater than 5. Does X equal 5? That's the equal comparison. X does not equal 5. Those are the kind of things we're looking for. We can see for loops do them. For loop has a comparison in it. So for loops have these comparisons. The if, we can see if definitely does. That's how we check on ifs. While loops do also. It's checking for whether or not something happens. So like, is swap true or false? Is it greater than or less than? So every time we have something like this, we want to implement some sort of count. So maybe we will have it. We're going to change bubble sort to be an integer. Let's do this. And we'll have it return the count. So counter. And it will return count. Let's make sure counter starts at 0. And we got to go in here. And so like going to the code, everywhere we see a comparison, we're going to add a count. So here, every time it goes through the for loop, we got to increment it. Counter is going to go up. It's not just on the first one, it's on the second one. We have it in here as well. We got 2 for loops here. Got nested for loops. And we want to count the if statement. What happens if we put the counter on the inside of the if statement? Will this be useful here? Let's think about it for a second. When does this part of the code trigger? Only if the comparison is true. And we don't want that. We want it to trigger every time, true or false. So, nope, not useful here. Don't put counters on the inside of an if statement. You can put it right before or right after, but it should increment outside of that. So I think I've got it done. Every time the for loop runs, it compares I versus n minus 1 or the size. Same here. Compares j to the size. And then this is the actual part where we are sorting. And we have to compare to see if we should sort. We should swap the order of the two. So it starts with the fresh counter, and every time it increments, it does it. And by the time we're done, I want to make sure this counter is outside. The return is outside all the for loops. It is. We're not going to worry about the print array. We just want to see whether the sorting array works. The print array is just for us. So this has a comparison, but we are only using it to show the technique. So we won't count it. Unless it's part of the native program that you're using it for. This is just to check how well the sort works. You don't always need a C out to have the sort. So we're not going to put a counter in the print array. Here, it returns something, so I could probably combine this and put this in here. And not have to actually do the sort right there. I think I can do the sort right here as part of it. And it'll return the amount and sort at the same time. An array, sorting a sorted array, and sorting a reverse sorting array. There we go. Now I got it telling us what it's doing. So the program is a little easy to read when we run it. Let's see if that'll work. It did. Look, sorting random array took 75 comparisons. For the random sort, it took 19 for the top one. Now it's going to take this same, I didn't seed it, so we can see sorting an already sorted array was much quicker than one of the other ones. Let's make sure we've got, what do we got to include for random? Does it include random? I don't remember this shit. Is it seed random? What is this here? I'm brain farting on random seeds. I'm null. SRAND, not seed rands. SRAND time null. Okay. or times 0. That'll work. That took fucking still 75, 19, and 99. There was nothing random about. There was nothing random here. I didn't randomly generate anything. I don't know what the fuck I'm talking about. And I got that up there in the wrong goddamn thing. Even if I did. Let's make a real random array. Call it Rando. Rando Calrissian. As a joke on Lando Calrissian. One plus rand mod 10. Such a nerd. All right. So really random took 96 there. These were already sorted, so these weren't going to change. The 1999 weren't going to change. Let's do it a couple times. See how it is. That one was a 91. Oh, fuck, that was a 99 also. 96. 84. All right, so I'm noticing something here, and let's bring up this and talk about this. So I got this worst case thing. And we're looking at bubble, and I can clearly see that the bubble sort, the best case scenario is pre-sorted. And the worst case scenario was reverse sort. And I don't know that average was much, I don't know that random was much better. Random might be just as bad as worst. Or random might be just as bad as random or reverse. But I'm doing one at a time. Maybe there's a better way of doing this. But I do want to point out something here. We had size equals 10. That's right. We had size equals 10 and reverse was 99. Which might as well be 100, which is basically 10 squared. And if we look at it that way, or size squared, let's say n rather than size. And sorted looks like it might be like 2n. There's an easy way to check this. We increase the size of the array. Let's do that. Is it 2n? Is it that what it's doing? Let's make this size 20. This should be changed to size. $20 squared should be 400. So we should see 399. Look at that. So we see 399 here when I put in 20. That's not what I want. That's what I want. Oh, come in here. I want to go. Well, look at you. You look fucking fancy. Oh, that's one of my Frixion pins. So when n equaled 20, let's call it n2 equals 20. We had reverse was 399, which is basically 400, which is 20 squared, or n2 squared. And sorted already was 39, which is like 40, which is like 2n. So when I did it like that, and it looks like the top one, 396, is still pretty close to being, it looks like random is just as bad. Random might be n squared also. Is random n squared also? Let's try it. Let's run it a few more times. See if we ever get anything a lot lower than that one. Took 399. I'm just checking the top row right here. 375, 375, 336 was a lot, not too much lower. Still in the 300s. Trying to do this like the way I'm doing it isn't a good way of doing it. So, like maybe we should like do it a bunch. Let's use what we know of science, statistics, the law of large numbers. If you do something enough times and take the average of it, the average will show you the long-term probability. So I'm going to do like a mega counter here. Yeah. Int total. Maybe we'll call it total rando, total sorted, total reverse. And we want each one of these to start off equal to 0. And I'm going to make some temp things. And temp rando. Temp sorted, temp rev, and maybe loop count or game count. We'll make this a constant one. Let's say we're going to do this 10,000 times. And I'm going to do while. Loop count is less than game count. Let's do this. And I'm going to put a loop counter in here starting at 0. All right, what we're going to do is we're going to move this thing in here. And each time we want the loop count to go up by 1. We want to run this. The idea here is run this 10,000 times, add them up, find the average. So we need to do the bubble sort. The bubble sort is going to return number. So this is the rando one. We're going to say the bubble sort, we're going to add it to total rando. And we'll do this for each of the other ones. Does what I'm doing right now make sense that I'm trying to find the average of the long run? Well, we don't need to do it on this one. With these two don't matter. They happen every single time. That's the same every time. The only one that changes is the random. These are fixed runs. So when we're going to do here, what we're going to do is we're going to do total rando after everything is done. Divided by game count. That should tell us the average number of trials it took each one. Does that make sense, Caesar? Like one of them took 336, another one took 375. We're going to add all those up, every single total trials, do it 10,000 times, divide by 10,000, then we can get like the average of how much each one took. That's the idea of what I'm doing right here with this sorting random array. I guess I only needed it for the random. I don't need one for temp sorted, temp. I didn't even need a temp anything. Because I was doing temp so I could print it out each time, but I'm not. Let's see. I think that might work. I got loop count rando 10,000. I mean, we could start at something small, start at 100 count or 500 count. Let's see if my idea is right. So if my idea was right, it's doing the average. This 370 shouldn't change much each time by the law of large numbers. 371, that didn't change much. 370. 370. So n equal 500 was enough. 369, yeah. We're all right around 370. So it looks like random is like n squared also. So random might be up here with reverse sort as well. I don't know what's considered average for a bubble sort. Let's go check Wikipedia. Oh, this leads the idea to big O notation. Big O notation. Counting comparisons is something that we do. Computer science is done for a while. And the O here stands for order. Like on the order of or magnitude. And the way they do it here, they would say for bubble sort, and we just showed this, and I'm sure Wikipedia is going to agree. The worst case scenario will be O(n) squared. That's how they show work. That's how they do order. This is called big O notation. Best case was pre-sorted. And it looked like 2n. I mean, you could say n squared minus 1 or 2n minus 1 because it was 399 and 39. And when we only had 10, it was 99 and 19. But they'll probably only have this and this. This is called big O notation. And this is how we decide speed and efficiency. And I'll show you something on that in a second. Let's go look at Wikipedia on big O notation. Not big O notation, the bubble sort. Wikipedia bubble sort. Thinking sort. That's an interesting name. Look, they've got listed over here, and they've got O(n) squared. Best case, they said O(n), not O(n). The idea here is uh, 2n is in like the linear category. So they just say O(n), and this is anything that comes in the form of mx plus b. Worse, this one is in like a quadratic form. So like ax squared plus bx plus c. What else did Bubble have here? So I said worst case was O(n) squared. Best case we're doing on comparison. So O(n) looks like swaps is another way they do it. Average was O(n) squared. That's what we saw for the random. And it's got a little animation showing how it works. It's kind of neat. That's the idea of what we're doing here, code efficiency. Does that make sense?
Yeah, it makes sense.
Okay. So what we want to do, let's come over here and let's look at like let's look at this again, see this again. I almost think fucking heap is heap fastest? Heap quick 3? I can't tell. Shell was done super fucking quick. Shell might be fastest. What is this shit? Shell might be fastest. Huh. Maybe we'll look at Shell later. What's quick 3 do? Does a three-way partition. That might be complicated. Let's look at just quick for now. Wikipedia on quick sort might be better. So quick sort is an efficient general purpose sorting algorithm. We can see pictorially what's happening here. Let's it starts off, it's random. What it does is it finds the last one size and it sorts everything into two halves. Wow, it happens so quick, it's hard to. Let me retry it. It's going to sort into two halves. Watch. It's got one half. The first half is less than the size. The second half was greater than the size. Then it goes through, and in the first half, it does it again. So maybe I can. When I back again, let's go back. They got more down here. So what they do is they grab the last one and they break this thing into two groups, two partitions. And they use the last one as something to check against. So everything that has a value less than 4 is going to go before it, and everything that has a greater value greater than 4 is going to go after it, but they don't sort it other than doing those groupings. So here it checks 4 versus 5. And says 4 is less than 5. We're going to swap 5, and it does 5 versus 7 at the same time. And it swaps 5 and 7. 5 is less than 7, so it switches there. Then it goes 4 versus 9. 4 and 9. 4 needs to switch. 9 is greater. It just forces the flip right here. So it's not actually checking this 5 versus 7 because it automatically forced 9 to switch with 5. Maybe it's checking these two right here, 3 versus it. Then it goes 4 versus 1. Oh, it moves 4 down. It checks 1 versus 9. It switches the 1. And then since 1 was less than 4, look at this. It stops checking the second index and starts checking the third index. So it keeps moving it. What it's doing is it's checking these two versus 4. That's what it's checking. It keeps moving 4 one position to the left, and it goes, okay, we're going to check the one right before 4, and the first index is assumed to be less than. I think they have it's part of the algorithm. If not, they swap them in the beginning or something to make it that way. And then as soon as the next index is less than 4, they stop using it and they go to 8. And they check these two versus 4. Whichever one is less than 4 goes in the left spot, and whichever one is greater than 4 goes in the right spot. And eventually 4 gets down into the middle. And then they break it into another quick sort with 3, 1, 2 right here. It sorts on 1. The 2 and the 3 have to switch places because one moves further, or 2 is the one it's checking. So 2 is it's called the pivot. They move the pivot back to here and they go 1 and 3. Which one's less than 2? Which one's greater than 2? It puts the 1 and 3 here. Then on 7, 7's the pivot. They're slowly moving the 7 to the middle spot. And as they do it, they're comparing to see which ones are less than 7. 5 is already less than 7. It leaves it alone. 8 and 5. 5 is less than 7, but 8 isn't. So it swaps the 5 and the 8. So if a bunch of these in a row are already less than the pivot, it should skip it right away. Like here, it didn't even pivot. There did no swapping or anything. This is called the quick sort. It's a little fucking confusing, but thankfully, there are enough geeks out there that did this already. Quick sort algorithm. Oh, let's put C++ on there. That way we get a good geeks for geeks C++ sort. Still similar to the merge sort algorithm, the quick sort algorithm is a. You're gonna make me fucking say I want to log in again. I do not. It's a divide and conquer, so it keeps splitting it into two different groups, and each little group, once it's done sorting the two or separating the two groups, it starts doing each of the smaller groups down until it gets smaller and smaller and smaller. It so quick sort always picks the first element as a pivot. The other one, oh, it just says there are many different versions. One always picks the first element, one always picks the last element. The one we saw on Wikipedia picks the last element. Some of them pick a random element. Some of them pick the exact middle of the array as the element. And it does this partition thing. And we saw that in this says that we got the implementation of the C++. Let's borrow this code right here. I think we need all of that. And then the main just has it testing. I'll come back and grab this part right here in a second. Let's come over and drop our, there's our bubble sort. Let's drop our quick sort in. So let's see. Let's make a comment about this. So I'm probably gonna be uploading this. Oh, I hate that. There we go. I like it like that. Partition goes with quick sort. So start and end. Looks like what part of the array does it want to sort at? Let's go back and look at Wikipedia or here. Oh, it starts at 0 and goes up to n-1. This is saying how big of the array do we want to sort? Because quick sort acts recursively. As we can see, quick sort is calling on itself. So P does the partition, it splits it into that two groups I was talking about. And then each subgroup, we got this group over here and this group over here. We start focusing on this one. It starts sorting this one. It does that into two, and then that and splits it down. And each one, it does a quick sort on each of the individual partitions as it goes until it gets down to the bottom. So rather than retyping that, I'm just going to copy this and add this right quick down here. Right here. Just throw it in real quick. I'm going to call it total rando Q. Quick. And we didn't have n, we have size. Oh, not equals, plus. Quick sort. What's wrong with it?
We haven't implemented a counter in quicksort.
Oh, you're right. And it's not returning anything either. Look at this. You go. I'm like trying to put the cart before the horse. All right, so if start is greater than n, hit just return. That is a check. So we need to do a counter there. Ooh. Partition is gonna have the partition is where it all happens. So maybe we're gonna change partition to have the counter coming in as well as a reference. We'll call it count here, so it's got a different name. And I want to make sure we put it in, but I gotta make sure when we're passing it, where is it? Quick sort passes, and we're gonna pass counter. Okay, come up here. It's got its own fucking count. Son of a bitch. My count. Call it my count. Or and I don't know, big O. So for in the for loop, we need big O to increment because every time it runs, I'm not gonna call it big O. I'm gonna call it the big O counter. So every time the for loop runs, it triggers. Then it does an if statement. Every time the if statement goes, it triggers. And this happens. It's got to do it at least once when the while starts. And this one, it actually does two comparisons there, doesn't it? It's got to compare I versus pivot index and J versus pivot index. And then it does it each time. Maybe I'll add these two at the bottom. After the while loop. Okay, so these are, if it only runs once, it happens there. If there's nothing going on, if the while loop doesn't trigger, but it still does the comparisons, it still does that counter there. Then we got the counters on the inside. That has to run every time that one goes. it's going to have it, it's going to check at least once. And it's incrementing. I think it's got to go in here too for each additional time it runs. Same with the J loop. It's checking to see if it swaps the last, where it's checking it's going to keep moving the pivot to the left to make the partition. But like as it's checking the first entry and the entry before pivot, it's doing each of those comparisons and going, should we swap those? I think we need a counter on each of these. And then we have 2 counters on that because it's got a double count. It's got the and here, so it's doing 2 comparisons here. This looks like there's a lot of fucking counters here, isn't there? That's a lot of fucking. Oh shit! It returns pivot index. Oh, well, that's good because we passed by reference. So we don't have to return the pivot. We don't have to return our counter because it's automatically updating the big O counter when it's called down here in quick sort. All right, let's make sure I did this right. We got our big O counter. It starts as 0 in the main or whatever it is. Comes in here. Let's say it starts at 10. Every time the for loop runs, it goes. Every time the if loop goes, it goes. Then there's nothing happening right here. We should check swap. This while loop triggers twice, and we put that at the bottom. While loop always happens once, so I put it at the bottom. And then for each additional time it happens, like if while happens twice, it will only go through this loop once. And then we got another one down here. We got the same thing going on here. Got that going there. I think we got it going, and then it returns the counter up here, and our total count gets returned into the main. And now it's not mad. Look at that. It's not mad. We have that thing up there. Let's add some more to our little thing. And now we're going to do these back to back. So sorting in a random way with quick sort. Did I have a total quick? I got total rando quick. So this will print this will do our 2. This has our bubble sort versus our quick sort. And then let's put some lines in here, make a little gap. Bucket. Got a C out here. First, we compare. I guess I should have caps lock. An array. in bubble sort versus quick sort. I guess I don't need that line each time. Next, we compare the sorted array. Trying to make it look pretty when it goes to screen. All right, now for each of these, I got to implement just need to, I don't need to do that twice. That's the one I want to get rid of. Let's get rid of that one. And this is the line we want to copy and edit. Oh shit, what happened? Fucking Zoom windows in my way. Copy. Okay. Sorting is sorted away with quick sort. Oh, quick sort, right? Quick sort, yeah. And I'm going to copy that line and edit this one. This one seems like the easier one to change. Sorting a reverse sorted array. I think I got it all. Just trying to make the printouts look good. Ah, sons of bitch. Line 165 and line 85. Okay. What's wrong with line 85? Oh, I don't have it set up right. I gotta do 0 and /1. There we go. Nope. Line 90, 116, 85. Line 90, is line 90 not returning a value? That's what was wrong. It wasn't a void. It was we changed it to an integer, so it's got to return the integer. Oh, we got way too many spaces here. Let's redo this. Okay. It's in our printouts. We don't need this to have as much space between it. A long line of fucking text. God damn it. Okay, first we could. I don't like the way that looks, but we'll change that a little bit. Bubble sort took 368 for a random array. Quick sort took 58. This was our average calculator. So that 368 is near the 370. Here, it looks like the sorted array between bubble and quick sort's about the same. But look, the reverse sorted array was just as quick with quick sort. So we're looking at 368 versus 58. Do it again. Yeah, it's still 58. That was at n equals 40, so it looks like maybe, or n equals 20, so maybe quick sort takes 3 times n. I don't know. Let's check. Let's change size up to 100. I don't need this line of code anymore. We didn't use it. All right, so we had n equals 100, and the quick sort took 300, so about 3 times. 300 squared is why did the wow, look at how short some of the no, n equals 100, so not 300. 100 squared is 10,000. So 9,675 is close to 10,000. That's n squared, just like we saw. N equals 100. They're both about 2n on bubble sort and quick sort. Quick sort has 2 extra steps, probably because I don't know, the way I set it up. Quick sort on the reverse sorted array is also on 2n. So like reverse case is a best case scenario. So it looks like worst case for quick sort. Does reverse sort have a fucking worst case? We got 201, like this was the worst, 305 out of the quick sort. I don't know. Let's change it to 1,000. N equals 1,000, which would be 1,000,000 for the other ones. For n squared would be 1,000,000. Oh, that was my bad. Maybe I don't need to print out the array. So 1,000 times 3, yeah, it is about 3 times n. That's close to 1,000,000. We check this. These are both 2n again. And that's 1,000,000 versus 2n. It looks like quick sorts definitely a lot faster. Maybe if I'm going to have it that big, maybe I can comment out doing the print array. Let's go take a look at Big O's notation, or the quick sort notation for Big O. Where is it? It's up here. The worst case is n squared. I wonder what the worst case is, because we didn't see an n squared. N log n or big O big N. N log n, that must be what they're going with. Huh. Does it say what the worst case scenario is? It doesn't. So n log n is n times log n. If it doesn't have a number, it's log base 10. So log base 10 of 1,000 is 3. So we had 3n. So I was writing 2n and 3n and shit, but it was really n log n. Because I'll put this right here. Log 10, 100 is 2. Log 10, 1,000 is 3. So 1,000 times log 1,000 is 1,000 times 3 is 3,000. That's why we were getting 3,000 on that 1,000 run. And I didn't see, I don't know what's going to make it the worst case. Does it say worst? What's worst in here? When the array is already in order, it's the worst possible case. We didn't see that when we were running it. I wonder why. Am I unknowingly changing the array? Let's put the quick sort first. I didn't, I need to change the spacing issues. Yeah, I'm not seeing what they're talking about. So maybe this quick sort algorithm that we're doing is the most perfect case scenario. Let me change the order again. There we go. I don't think I need as many spaces. That looks kind of trashy. Make it look less trashy for what we share with the class. There we go. That doesn't look so trashy. Oh yeah, we already knew bubble sort was shitty. So this big O notation, let's come back to our thing in class right here. If you click on the big O notation PDF, this is kind of neat. So it's got a comparison of how quickly they grow. Log 2n is looks like better than n. Then there's n log base 2n, n squared, n cubed, 2 to the n. And it's got them listed down here. So the speed is based on this order. Order 1 is just constant. There's no matter what size the array is, there is a fixed amount of comparisons. I can't picture something that has that. There must be something. For a lot of things, for the average case scenario, n log n tends to be the best we can do, which is what we saw in quicksort. Quicksort average had n log n, but when we checked bubble sort, the average was n squared. So coming up back over here, everything that they've done in computer science, n log n is about the fastest they can do. I don't know why they're doing log base 2, because it's clearly not log base 2, it's log base 10. We just showed it was log base 10 based on n. We like calculated it, we ran it. So some things like grow faster than others. The lower this thing is on the table, the less operations it takes and the faster the code's going to run. Because every time it does a comparison, no matter which processor it's on, which computer it's on, it takes the computer, whatever for that computer, takes a specific amount of time. And so you're counting those things and you want as few as possible. Does that make sense? So there's a couple of arrays, but there was a lot of different sorting algorithms we could have checked. It'd be fun to go through. You could look up the other ones, see how they work. Shell looked pretty fast. N4, is that n to the 3 has? I don't know what that means. N log 2n. Be fun to see how some of those work. So some of your labs in this section are implementing this counting thing. This is worth a good run through. That might be Professor Redden's. I borrowed some of his stuff here. Some of this stuff might be worth looking at. When you're doing it, don't include the while user input equals y, like the replay the game thing. Don't include that. Because that's just if they're playing the game again, the game's already been played. You want to check the single run through once. And let's take a look at some of your labs. So you're going to make an integer based vector, and you're going to have it. We were doing sorting algorithms, but you're going to do search algorithms. A linear search and a binary search. Let's see. Let's go back. Got the heat. It's not what I want to check. Oh, this method 1 says, scroll down, there's another one that says method 2. I wonder if this is a different quicksort. There's a lot of things that fall under the quicksort situation. All right. We've done linear search in other modules. Let's go back and look. We did the binary search here. So you've done this on lab 2B. I'm pretty sure linear search is just going through them left to right until you find it. I don't know, what the hell is the linear search? I'm brain farting. Yep, just goes through it, tells it finds it. Now, on these, I still need to add, did I add the video? Nope, exception and try catch is there. Okay. Here you're just setting up the thing for the counting, but there is no counting yet. Right now, you're just implementing the quick sort or whatever sort you want, choosing any sorting method of your choice. You do need to sort because binary requires a sorted list. Print out the vector, show what it is, and then have it. What you're doing is you're searching the vector for a value. So however you choose to implement it, do as you wish. You might make, like when you make your random vector before you sort it, you might say, let's make target equal whatever is in index 50. And then after it sorts it, you don't know where index 50 moved to. And so that's a quick way, because if you're doing random integers, you want to make sure your target's in there. Well, I guess you don't have to. You can say don't do that. If you want to make sure it's working and finding it, make it choose like target equals array 50. But after that, the general one should be just target is random 100. 1 plus random 100. That way you're looking for a random one, and like if it doesn't find it, that's like the worst case scenario in general for searching for anything. If you're searching through an array or a vector and it's not present, it's going to have to go through the entire cycle no matter what. But in the first lab, you're not doing any counter. The next lab, you're implementing the counters. And just how to do it for both of them, linear and binary. And then the third lab is, I think, doing the average. Yeah, like I did in what I presented here. I didn't do 100,000. I just did 1,000. I don't know that you need that many, but you can't. I do at least 1,000. 50,000 is probably a better way to go. That way you make sure the law of large numbers kicks in, and it doesn't need to be that big. 1,000 is enough. And then give the try on the merge sort. So maybe not do the merge sort on the first one. Like have experience doing different sorting algorithms. Try the different ones out. I realize that this is, as you saw me do, I stole quick sort and bubble sort. I encourage you, you can do that in this, whatever sorting algorithm you use. Go steal the algorithm from Geeks for Geeks. It doesn't come with it implementing a count in it, so you have to adapt it. And you've got to make some main function that drives the whole thing. So you're going to have a lot of your own code in there, but you're free to go steal the code to do the sorting out algorithms quicker. Okay. Any questions? Control A, Control C. If we got no questions, I'll call that a wrap. That was shit, 3 to 5. That was like a 2 hour lecture. That was your Friday lecture that we missed. I had people working on the house that they ended up taking longer, and I wasn't gonna be able to make it. We're redoing our front lawn, and putting up a fence, and so our puppy can go out and play. And they just ended up being here longer than I thought. That's all I got for you. I'll stop recording. If you got any questions, now's the time to ask.